Okay, so welcome to the second part of the lecture about land cover change detection using remote sensing. In this part, we will talk about the requirements of the data that you use for detecting the changes over time. And there are some different parts which you need to consider. For doing a successful change detection, it requires that the data have some constant resolutions. For example, the temporal resolution needs to be the same. The data of the first image and the last image needs to be taken up at approximately the same time of the day and at approximately the same time of the year. The spatial resolution should be the same so that the both images have approximately the same pixel size. The angles which the data is recorded at should be at approximately the same, and the spectral characteristics of the satellite sensor should also be the same, so that the red band is recorded at the same wavelength for both sensors, both the first image and the last image. If not, it might be that the changes that is detected in the analysis is based on variation rather in these factors and not changes in the land cover itself. So, first of all, when selecting two images, it's important that the temporal resolution is the same. The data should be recorded at approximately the same time of the day. If not, say that this is a Landsat 8 image, Landsat has an overpass time of about 10:30 in the morning, which would mean that the sun illumination angle is coming from slightly lower angle and coming from the east. Whereas if we, in the second image, would use like a Sentinel, for example, the overpass time is 13:30 in the afternoon, and which would mean that the illumination angle is coming slightly, relatively high up in the sky and seen it, and maybe slightly coming from the west instead. So if possible, it's good if both images are taking up at approximately the same time of the day, which would mean that the illumination angle is the same. So the differences between the images is not caused by these illumination differences. Secondly, it's good if the same date, if the data is recorded at approximately the same date of the year. Since, say, during winter time, we have a quite low amount of vegetation, so the vegetation index values are low. And then as the growing season starts, and the VI, for example, whatever vegetation index we are using is increasing, it peaks at the middle of the growing season, and then during autumn, when the vegetation starts to senescence, the vegetation value goes down again. So, say that this image would be taking up in the beginning of the growing season, we could have a value here, and the second image would be taking up at the peak of the season. This would, of course, have very different NDVI values for these two different images. We would rather be caused by the changes in the phenology of the vegetation rather than an actual change in the land cover itself. So the next thing that is really important to think about is the spatial resolution. Ideally, change detection should be done with data collected with the same spatial resolution. Say, for example, that we have an image recorded here in 1995, and then we have another one recorded here in 2005. In this one, we have a spatial resolution of 1 kilometer, whereas here it's 250, 250, 250. Perhaps all of this pixel would be covered by forest, part of this would be covered by forest, and part of this would be covered by forest, and part of this would be covered by forest. In this case, all of this could have the value of forest, whereas in this case, This one would have forest, and here maybe the rest of this one would be a lake, and the rest of this one would be a cropland, and the rest of this one would be urban, for example. When doing a change detection between these two different points in time, it would indicate that we have change detection, but perhaps it was always the same amount of forest and the same amount of lakes and urban and agricultural areas, but just because the spatial resolution was different, the analysis indicated that there was a change, when in reality there were no change at all. So if possible, it's really important to try to keep the spatial resolution the same. This is not always very easy, since older images tend to have a larger pixel size than images of today. The second thing when it comes to spatial resolution is misregistration of one of the images. Say that you have a river that runs through your area that you are studying, and then you have one image from 1980 and another one from 1990. If one of the images have been misregistered when doing the georeferencing, this can have really big consequences on a change detection analysis. Say that we have a misregistration of one single pixel. This would cause this complete river to be considered converted into, for example, agricultural land, whereas it would also consider all, if this would have been forest, for example, all forests gone and instead converted into rivers. So this, of course, would have a big consequence for your analysis of land cover change detection. Another thing that we need to consider is the viewing angle of the sensor. We have previously discussed the viewing angle of the sun, but the viewing angle of the sensor is also very important. We can see this is an example here of a photo taken from the top of a tower on a savanna landscape. And you can see here, when looking close to the tower, it looks like the landscape has pretty much soil and not very many trees. Whereas when looking closer to the horizon, we can see that, oh, it looks like it's really green, this landscape. It's a lot of vegetation here. So with a higher viewing angle, more of the vegetation is seen, generating more vegetation in the image compared to an image taken with a lower viewing angle. So therefore, when comparing two different images, it's really important that they are taken with approximately the same viewing angles. At this tower here, we have a sensor that is measuring NDVI in different angles. And we can see then that when with different viewing angles, we get different amount of NDVI depending on the angle of the sensor, simply. Finally, we have come to the last part of the requirements we need to consider when choosing our images to do a change detection analysis. And this is the spectral resolution of the sensors of the satellites. Here we have the wavelength of the radiation that is absorbed by the different sensors. And you can see here that, for example, on Landsat MSS, the sensor that is recording the red band, it records all the radiation that is reflected from 0.6 to 0.7 wavelength, micrometers, sorry. Whereas the Landsat TM, it has it absorbs the radiation between 0.63 and 0.69. So you can see that this could generate actually quite different information in the different bands. And this is even worse when looking at the near bands, because near of MSS has a spectral resolution of 0.7 to 0.8, whereas in Landsat TM it has a spectral resolution of 0.76 to 0.9. And this is, so these different images has quite different information in their different near images. So if we then compare an image from Landsat TM with a Landsat MSS, when we are doing a change detection analysis, it could be that the actual differences is not really caused by a change in the land cover, but it's rather caused by a change in this in the wavelengths which is recorded by the near band in the different satellite sensors. So this is the final thing which is really important to consider. So to conclude, when doing a change detection analysis, you need to make sure that the sensor system have the same temporal resolution. Images are recorded at the same time of the day and the same time of the year. It needs to have the same spatial resolution so that different things are not included in the same pixels that are compared. It needs to have the same viewing angles so that we are actually looking at the same part of the ground with both the systems. And finally, that the spectral resolution is the same so that what is considered the red band or the near band in one of the images is actually the same red and near information in the other image. Thank you very much for listening to this part, and we'll now take a short break and come back with part number